Good morning, everyone, and welcome. Thank you very much for joining us today for the final online event of the Life in Desal project. It's a real pleasure to see so many participants with us this morning. I see people are still joining. We have way more registrants. I think maybe they're still grabbing their teas and coffees. Thank you to all of the speakers and participants joining. We have today with this morning project partners, researchers, innovators, representatives of related EU projects, stakeholders working at the forefront of sustainable desalination and water management. My name is Micaela Martirosyan, and I will be hosting alongside ACCIONA team today for the webinar. As many of you know, water scarcity is becoming one of the most pressing challenges across Europe and beyond, especially in coastal and Mediterranean regions. Desalination is increasingly part of the solution, but it must become more energy efficient, more circular, and more sustainable. And that's exactly what Life in Desal project is set to demonstrate. Over the course of today's webinar, we will present the key results and achievements of the project, explore circular and innovative approaches to seawater desalination, hear from related EU-funded projects, discover breakthrough technologies, and take you on a virtual tour of the Life in Desal pilot plant in San Pedro del Pinatar. Before we begin, a few quick housekeeping points. So this webinar is being recorded. You're more than welcome to submit your questions at any time in the Q&A section in Zoom. However, we will address them during the dedicated Q&A session. We will start with the opening session where we'll set the scene for the day and present the overview of the Life in Desal project and the results. So it's my pleasure to pass the floor to Mariana Figueira Alves, who will present the Life in Desal overview and key outcomes. So without further ado, Mariana.
Thank you, Micaela. I'll share my screen. Yeah, so thank you all for coming. We're very happy to have you all here today in our final event of INDESAL. It's a project very dear for us. And I'm Mariana Figueira. I work in ACCIONA Water at Innovation Department in the Desalination and New Technologies team. So I will present today the overview and main results of the Life in Desal project. Yeah, as Micaela said, we have a great concern regarding water scarcity. So the number of regions that suffer with water scarcity had increased in the past decades due to the increase in water demand imposed by population growth, increase in agriculture, industry, and energy consumption, and also due to effects of climate change. And the prediction is that this number of regions will increase in the next decades, the regions that suffer with water scarcity. So in this scenario, desalination is a very important technology because it provides high quality, reliable water that can be produced even in regions with water scarcity. And this is a technology that's already very important nowadays in many countries, and the importance will increase in the coming years. And for this future, we hope to have a more sustainable, more efficient, and more circular desalination process. And for this, we came with this project, the INDESAL project. So the objectives of Life in Desal are to improve the efficiency and circularity of seawater desalination with a novel integrated process. So here we have three pillars. First, we want to increase energy efficiency of seawater desalination, and for this, we proposed applying a low-pressure multi-stage reverse osmosis. And the second one is to generate renewable energy from brine. And for this objective, we propose the use of reverse electrodialysis. And for the final objective, to transform brines into chemicals needed within the desalination process, we propose the use of electrodialysis with bipolar membrane. And here we have not only the idea of increasing the efficiency of desalination of reverse osmosis, but also we want to give value to the brine, the desalination brine. So here the reverse electrodialysis and the electrodialysis of bipolar membrane will use this brine that before was considered a waste stream of the desalination process. And now we want to add value to this stream. So here we have an overview of the INDESAL project. ACCIONA is the coordinator, and we have as partners Apria Systems, University of Cantabria, REDStack, and Revolve, partners across Europe. We started this project in August 2022. We are finalizing this month, but well, we are still operating the pilot, and we have plans to keep the operation a few months after the end of the project. Our demonstration site is near the desalination plant, the seawater reverse osmosis desalination plant of San Pedro del Pinatar, which is in the region of Murcia in Spain, and it's located in the lead R&D facilities of ACCIONA. So LEAD is the leading experimental accelerator in desalination. We have other pilots there, all working with R&D in desalination technology. So this is the technological scheme of INDESAL simplification. We have real seawater entering the system. We have first a pretreatment and then the LMSRO, low pressure multi-stage reverse osmosis. So the permeate of the LMSRO is fresh water that can be used for potable, agriculture, and industrial. So here we have just the permeate. We're not doing the remineralization. We would need this step to have drinking water, but we can already check the quality of this permeate produced. And with the retintate of the LMSRO, the brine, we can have two processes in parallel, the reverse electrodialysis, RED, to produce energy, and the DBM, after nanofiltration pretreatment, we have the DBM to produce sodium hydroxide and hydrochloric acid that can be used in the cleaning procedures of the LMSRO. So here the low pressure multi-stage reverse osmosis is the technological expertise of ACCIONA. We have two passes reverse osmosis. So it's the principle is similar to reverse osmosis. We have seawater being pumped in high pressure against a semi-permeable membrane. So the membrane lets the water molecules pass and will retain most of the ions. So we produce like these two streams. The water molecules that pass the membrane produce the permeate, and the part of the water molecules with the ions that were rejected produce the brine. So we generate these two streams, and usually the brine was considered a waste of the process, but now we are valorizing this stream. So the LMSRO is similar to a RO, but we apply the shorter pressure vessels. So in industrial desalination, usually we have 7 or 8 elements per pressure vessel, and in the LMSRO we have up to 4 elements per pressure vessel. So with these shorter pressure vessels, we can have a better flux equalization between the elements, reduce the concentration polarization, and it's easier to tune the cleaning procedures because usually you need to clean the complete pressure vessel when you do a cleaning. And sometimes just one of the elements needed to be cleaned. And with shorter pressure vessels, we can save in chemicals consumption and water consumption for the cleanings if we can do it more directed to the elements that really need the cleaning. Yes, so the other technology that we have is the RED. I will not explain the RED in details because Hendrik will do this later. So RED is technological expertise here of REDStack and also Apria Systems. And well, the technology uses the ion exchange membranes and the salinity gradient. The driving force is the salinity gradient to produce renewable energy. And we have a flexible pilot. We can use 1 or 2 stacks. So we have 2 stacks in series, and we designed it in a way that we could opt for using 1 or 2. And for us, it's very interesting to use brine for salinity gradient, because the brine have a higher concentration than the seawater, so we can generate even more powerful salinity gradient using the brine from the Lamaçaró that used to be considered a waste of the process. And here we have the other technology, that is the DBM. It works in parallel with the RED, so the brine is divided for the two different pilots. Also, I will not explain in details the DBM, because Marina will explain better later. But here, it's a bit similar to reverse electrodialysis in the way that we have the ion exchange membranes, but here we also apply a bipolar membrane that's important for producing acid and base. And while the RED uses the salinity gradient as driving force to generate energy, here in the DBM, we apply energy. So it's an energy consumption process where the electrical field generated is the driving force for the ions migration. So here we want to produce sodium hydroxide and hydrochloric acid that can be used in the cleaning procedures of the Lamaçaró. And here is the expertise of University of Cantabria in Apria. And here you can see some images of our pilot. It's where it's located in the lead facility of ACCIONA. We have 2 containers, one on top of the other. So in the base we have a 40-feet container with the Lamaçaró and the pretreatments of the Lamaçaró. And in the top we have a 20-feet container with the DBM and the RED pilot.
And now I will present you some results that we obtained with the project. So here we have some results of the Lamaçaró part, and we can see the feed, the quality of the feed over the year. So the Lamaçaró was the first unit that we started the piloting. It is operating for 20 months. It's still operating, as I mentioned, and we hope to keep operation for a few more months. And we can see that we have a lot of variation during the year. So this is common with seawater to have a seasonal variation. So we can have not only due to summer, winter, but also due to storms like natural events, proliferation of algae, and all these affect the quality of the feed that enters our pilot. So we can see here that we have average temperature around 23 degrees, but in summer it can be even higher than 30, and in winter it's usually below 20 degrees. And we can see also how our pretreatment works. So the turbidity of seawater in average was 0.5 NTU, and the conductivity of 50 millisiemens per centimeter, and an SDI 15 of 5.2. And before entering the RO, after the pretreatment, we could reach a turbidity below 0.1 and SDI of 3.2. So our goal was to have SDI below 5 to enter the Lamaçaró, and we could reach this goal with the pretreatment installed. Also, we can see here the conductivities. So even though we have a variation of conductivity through the year, we could keep conductivity of the second permeate very low, below 200 millisiemens per centimeter. Also here we can see the flux and the recovery. So both were very stable. during the operation. So at the beginning, we were making a few more tests, so we had some fluctuation, but after we decided on optimal parameters, they were quite stable. So we have a flux in the first pass of 11 LMH and in the second pass of 26.5. And regarding the recovery, we have a recovery of the first pass of 44%, which is pretty standard for desalination plants. But in the second pass, we have a recovery of 54%, which is a bit low for compared to traditional desalination plants. But this we had to do due to space limitations. We couldn't design a larger second pass due to the space available in our container. But with in an industrial scale and scaling up the INDESAL solution, it would be easy to reach the at least 80% recovery due to the quality of the feed that enters the second pass. So here we have a global recovery of 33% in our system. We also have some results regarding normalized differential pressure, normalized permeate flux and salt passage. So the differential pressure was quite stable. The salt passage, we always had below 0.6%. We had established a limit of 0.5 for cleaning. So once the salt passage reached 0.5, we had cleaning procedure. The normalized permeate flux fluctuated more at the beginning of the operation, but after some months it also quite stable. And here we have the results regarding the quality of the permeate. So we had a goal to produce a permeate with TDS below 200, and we achieved this goal. We had an average of 180 milligrams per liter of TDSs in our permeate, and we start with 34,837. So it's a very robust system, can reduce a lot, not only the total dissolved solids, but also the sodium and chloride. We can see that we had the concentration below 100 milligrams per liter. And also we can see here the boron concentration. So in the seawater, we had the concentration higher than 4, like almost 5. And in our global permeate, we reached 1.5 ppms of boron without adding the sodium hydroxide in the second pass. So we had a change in legislation recently. Now the boron in drinking water coming from desalination plants can be up to 2.4 ppms. So we saw no need to add this sodium hydroxide to increase the boron rejection in the LMSRO. So without adding more chemicals, we could reach the 1.5 that is inside the limit established by the legislation. So we consider that we have high quality of permeate that is compatible with drinking water production. Of course, we still would need a remineralization step, but it's already very good quality permeate. So now also present some results of the RED. So as I mentioned, we are still operating our pilots. So these numbers are not final. We're still calculating, but this is what we have so far. So we tested the two options to have 2 stacks in series or just 1 stack. And we saw that with only 1 stack, we produce about 0.06 kilowatts hour per cubic meter of brine with 0.92 watts per square meter of membrane of power density. And with the 2 stages, we can produce more energy. So up to 0.12 kilowatts hour per cubic meter of brine with a power density of 0.64. So we saw that the first stage is more efficient to produce energy, but this was expected because when the streams enter the first stage, you have a bigger gradient between a bigger difference of salinity between the streams, and with the ions migrating, this gradient will reduce. But still, when they leave the first stack, there is still some capability to produce more energy. There is still a gradient that can be explored to produce more energy. So with the two stages, we could reach a higher energy production of by cubic meter of brine. Now, regarding the dBm, we can show here the concentration of the sodium hydroxide and hydrochloric acid produced. This concentration was sufficient for us to do the cleaning procedure, so it was a good concentration regarding what we were expecting for the cleaning procedures. As I mentioned, we are still hoping for final results of laboratory analysis, ICP results, to determine the purity of our acids and base. But regarding the concentration, we are already happy with the results obtained. So in conclusion, we have here the first objective to increase energy efficiency of seawater desalination. With our LMSRO system, comparing with a conventional reverse osmosis with second pass in similar conditions, like same quality of feed as our process, we obtained a reduction of 0.2 kilowatt hour per cubic meter of permeate in the specific energy consumption. Regarding the generating of renewable energy, we could produce up to 0.12 kilowatt hour per cubic meter of brine with the reverse electrodialysis. And we could, with the electrodialysis of bipolar membrane, we could produce 100% of chemicals needed for cleaning, making our desalination process more circular. So yeah, I would like to acknowledge all the Life in Desal team. It was a very good job over these years. Acknowledge the European Commission, the Mancomunidad de los Canales de Taibilla, which is the region where our pilot is installed. Thank you, of course, the audience for joining us, and the keynote speakers for the next session. Yeah,
Perfect.
so thank you.
Thank you so much, Mariana. We have some questions. We still have a lot of time, so we can take our time. So the first question is, what were some of the main operational challenges in keeping a pilot running for so long, and how did you solve them?
Yeah, I think when you run a pilot for so long with seawater, the main difficulty is this variation of the quality of the feed. So when you design the process, you should already have gathered a lot of information to design the process for the extreme condition, and also plan a pre-treatment that is robust. So this was our strategy. We planned. Sorry, I'll start my video. So we planned a system, a robust pre-treatment, and we had, of course, to analyze the quality of our feed and our permeate or our brine every day to adjust, to make the adjustments needed if we had to make some adjustments in the pre-treatment, the coagulation, everything. We had to do this daily. And it worked. We could produce with very stable permeate quality, even though the feed varied a lot. Our permeate was very, very stable.
Thank you. And the next question is, when you look at the trade-offs between energy savings, water recovery, and cost, how does it affect the three INDESAL technologies?
This is something very important that we must think in the global process. So if you wanted to have a higher water production, you need usually higher pressure, higher energy consumption. And if you opt for this, for increasing the permeate production, you will have a more concentrated brine. So when you look to the LMSRO, higher water production is means more energy consumption. But if you look to the red, if you have a more concentrated brine, you can produce probably more energy, more renewable energy, because you have the higher gradient of salinity. So it's matter of testing and see the optimal condition. If the production of energy in red can compensate this this increase of energy consumption in the LMSRO. And also we have the DBM. So for the DBM, we have a nanofiltration before the process. So if we have a more concentrated brine, also we may spend more energy in the nanofiltration. So all the all the processes are connected, and we had to make tests and optimize our system in this sense, to see that all the energy consumption could be compensated.
Then we have a question actually from, I think I can name drop, from Frank Newman, who was one of the speakers for our midterm event. Frank says, thank you, a great presentation. Can you tell something, if possible, about the pretreatment and issues with water quality and how they were solved?
Our pretreatment, we have 4 multimedia filters, and we have a coagulation step before the pretreatment. So usually what we do is to adapt this coagulation depending on the quality of the feed. And yeah, so this is the thing that we must analyze in a daily basis. And our filters, they work in parallel, so we can have, for example, one cleaning while the other 3 work. But yeah, it's not in a sequence. They work in parallel. And yeah, with these daily analysis, we could operate with very good stability.
Thank you. And then we have a question. Could you comment on the max temperature of the brine entering the EDBM?
Yeah, so this is something that concerned us a lot during the experimentation. So was a big concern for summer mainly, because in this region we have a very high temperature. So we installed the air conditioning inside the container. We installed also the coolers, but also we had to make an option to do not operate the DBM in August. Honestly, it was not needed, because we were producing chemicals for cleaning, so we were not producing continuously the chemicals. We were producing the chemicals we needed. So we made this option to don't produce in August, because the temperature was quite high and it was harder to control. But basically, this was our strategy. Avoid August and put the air conditioning, the coolers, because we were producing for our necessity of chemicals.
Then another question. I have a question on the quality of the NF permeate before the EDBM. Were the levels of calcium and magnesium compatible with the operation of the EDBM unit? Was it required any polishing pretreatment?
Our pretreatment was the nanofiltration. So now we have nanofiltration membranes that can remove even more than 90% of the magnesium, a little bit less calcium, maybe 80-70%. So the main pretreatment was the nanofiltration, but we also had these pre-filters before the membrane stack to remove any possible precipitates that could be formed. But we didn't do. Also, we have some pH adjustment to have more acid streams to avoid precipitation as well.
Thank you, Mariana.
Thank you very much.
So we'll move to the first presentation of related projects. The first presentation will be by Patricia Terrero Rodríguez from the HyReward project.
Well, good morning to everyone. And well, first of all, I would like to thank to Mariana, Olga, and all the INDESAL and ACCIONA team for inviting us to present our live HyReward project, which is very related, no, with the objectives of the INDESAL project. All of us know the problem of water scarcity that we suffer around the world, and desalination currently is one of the most important unconventional water resources worldwide, and promise to be the definitive solution, no, to address these water scarcity problems. But we have several challenges that we have to face in the sector in order to improve the efficiency and the sustainability of the technology. These main challenges are the reduction on the energy consumption, which is directly related with the cost of the desalinated water, and also the brine management in order to valorize it and also reduce the environmental impact, no, of its discharge. Then these challenges highlights, no, all the need to implement innovative technologies in the desalination process, in the RO process, in order to make it more efficient, more sustainable, and more circular. And this is the objective of the Live HyReward project, in which we have to develop a hybrid system of desalination for the production of renewable energy from the desalination brine. How? Combining the RO process, the reverse osmosis process, with the RED, the reverse electrodialysis, in order to increase the sustainability of the desalination, generating electrical energy with RED technology. No? And with this integration, we are going to be able to produce energy to recover the energy contained in the brine that we generate in the RO process before it's discharged into the sea, producing a clean and completely renewable energy. The process, or the project, sorry, is coordinated by SACIR, and we work in a consortium with two companies from the Netherlands, REDStack, that is involved also in the INDESAL project, and Pure Water Group. Mariana has presented us the RED technology, and for this I'm not going to explain it deeply, but you know that the reverse electrodialysis is a technology that allows us, no, the generation of electrical energy from the salinity gradient between two streams with different salinity concentration. No? And the energy produced with this technology is called blue energy, and is considered a completely renewable and sustainable energy without CO2 emission or other greenhouse gas emissions. And in the technology concept that we have validated in the Live HyReward process, we have used the brine of the RO process, such as high salinity stream at the RED process, and the treated wastewater, the effluent of a wastewater treatment plant, such as low salinity stream. Here we are going to see, no, the technology concept that we have validated in the process. Here you can see the general scheme of a desalinated process, in which the seawater is fed to the pretreatment in order to remove suspended solids or other materials, and is later fed to the RO process, producing the permeate or the water product and the brine. And this brine has a high concentration of salt, has a high potential energy that can be can be harvested in the R&D process. But for this, we need a stream with a low concentration of salts, no? And as I have said, in our case, we have used the effluent of wastewater treatment plant, the treated wastewater, no? And these two streams, the brine with a high concentration of salts and the treated wastewater with a low concentration of salts, we have fit the R&D process, be able producing or harvesting the total salinity gradient between this stream in the R&D process, generated energy, and also producing the dilution of the reduction in the salt concentration of the brine. And for this, we have studied another alternative of this technology concept, that is the recirculation of the diluted brine another time to the RO process in order to increase the total recovery of the water. Here you can see the two configuration that we have tested. The simple one, no, that is in the left, in which we feed the R&D process with the brine and the treated wastewater. In this case, we are going to generate electrical energy. We are going to generate electrical energy, reducing the total energy consumption of the global process, and also the reduction of the brine concentration before it's discharged. No? And if we recirculate this diluted brine, we are also going to improve the total water recovery, no, of the desalination process that is traduced in for the same permeate production or total water production. We are going to reduce the seawater intake and the pretreatment needs in the Desal plant. Well, for validate the technology and the technology concept, we have designed and built a pilot plant that you can see in this slide. The pilot has a total capacity between 1 to 5 cubic meters by hour, and is included in a container in order to be able to install it in different locations. No? Here you can see the RED stacks developed by REDStack, and for example the Electromembrane. And well, I have said we decided to install it in a container in order to test the technology in different locations. No? And we have validated the technology into different desalination plants, no? in two phases. The first validation was carried out at the Alicante desalination plant in the southeast of Spain. And in this phase, we have validate the technology. You have to investigate the production of the electrical energy in the R&D process using RO brine and permeate as a low salinity stream, because in this plant we have available real treated wastewater, so we optimize the technology using permeate in this case. No. And this experimentation allow us also to start with the economic study of the technology and identify potential challenges for its implementation at full scale. Well, then the objectives of this phase was, I have said, the validation and optimization of the R&D technology for maximize the blue energy production using permeate as low salinity stream and brine such as high salinity stream. Here you can see the main results that we obtained. We have carried out a full characterization of the stacks in different scenarios with different ratios and flows of brine and permeate, no, in order to characterize the stacks and determine the best conditions in terms of total energy production and and salinity reduction in the brine. No? In this case, we have obtained a maximum energy production of 0.31 kilobytes hour of blue energy by cubic meter of brine. And if we could install the technology at full scale, with this total energy production, we could cover the 66% of the total energy consumed in the pretreatment. So it's a very important ratio, no? And also we have obtain a reduction in the salinity brine that is depending on the ratio, no, and the combination of flows between brine and treated wastewater. But we have obtained salinity, brine salinity close to 35 grams by liter, similar to the seawater levels, in order to be this potential recirculation of the brine another time to the ARO process. And well, once we finish the validation phase in Alicante, we move the pilot and install it at the Alcudia desalination plant in Mallorca, in the Balearic Island. And we decided to transport the plant because very close to the desalination plant, we have a real wastewater available, and it will be possible to validate the technology using real wastewater. No? For this, in this phase, our main objective was to validate the technology using real brine and real wastewater, and also study the effects of the use of wastewater in the R&D process, no? Such as the potential crossover of micropollutants, of contaminant of emerging concern from the wastewater to the brine, and also investigate the potential pathogen reduction in the discharged wastewater due to the osmotic shock, no, that the pathogens could suffer during the process. Well, here you can see the main results that we obtained in this phase. I would like to say that in this phase, we changed the membranes that we use in the R&D process. We changed the R&D membranes because in Alicante we saw some leaks, no, in the membranes. So we decided to replace the membranes and install another membranes with a more compact designs, and compare the results obtained with both kind of membranes. No, so in this case, with these new membranes, we will be able to reduce the leakages in the process, but we obtain less energy production. It was the main impact. No, in the next slide, we are going to compare the results between Alicante and Alcudia, and we will see the total values. No, but for example, if in Alicante we obtain a maximum January production of 0.31 kilobytes by cubic meter of brine, in Alcudia we obtain a maximum production of 0.24. No, due to the higher resistance of the membranes to the energy. Another results that we saw in this case regarding, for example, for the analysis of pathogens, we obtained an important reduction of all the species that we have studied. In fact, for example, in the Legionella, we obtained a total reduction of the presence in the wastewater at the output of the RET. And well, here you can see all the comparison, no, of the energy production obtained in Alicante and Alcudia. And I have said we have obtained a lower energy production due to different factors. First of all, in Alcudia, we have a lower salinity gradient between brine and wastewater because wastewater has high salinity than the permeate of the RO process due to some marine intrusion that we suffer in the area, such as as the salinity gradient was lower, the energy production, of course, was lower. Also, we obtain higher ionic efficiency of the membranes due to the new design that we installed in the RED process, but we obtain lower energy production due to the higher energy resistance. But we be able to reduce the leakages that we suffer in Alicante. For this, we prefer not to use the second model of the membranes. And well, to sum up, with the HyReward project seeks to improve the energy efficiency of the seawater desalination while it optimize water recovery, reduce the brine discharge, and minimize the use of chemicals, promoting a more efficient and sustainable solution, focus on the circular economy and water resilience in water-scarce regions. And the proposed hybrid RO-RED approach represents a sustainable and efficient solution aligned with circular economy principles and designed to enhance water resilience in regions facing scarcity. And the favorable results position the life HyReward concept as such as a promising technology to support a more sustainable future for desalination. Here you can see the main data of the project. As I have said, is a project funded also by the LIFE program. Sathira has been the coordinating, and we have worked in a consortium with REDStack and Pure Water, and the project has finished recently in October of last year. Well, this is all. Thank you for your attention.
Thank you so much, Patricia. Now we'll move to the next presentation, and we'll have the Q&A session. I see already a lot of questions to you, but we'll keep them for the Q&A. So the next presentation, I'll pass the floor to Klaasjan Raat with the Life Freshman Project.
I think you can hear me. You can see my screen as well.
Indeed,
Good.
yeah.
Good, thanks. Hey, and thanks, Michaela and others for providing the opportunity to present a bit about the Life Freshman project that has finished in December this year. They were still writing up some last final reports. And I have a background in water resources management, so I'm not into water treatment, though I have quite some experience and I know of membranes, of course, and what is going on there. And also this presentation is about membranes, but it's also about water resources management. I will take you to the dunes at the Dutch coast, the coast of the Netherlands. You see here the city of The Hague near the beach. You see the pier, the boulevard, but in the background you see the coastal area of The Hague. And in the Netherlands, for cities like The Hague, but we have similar systems for Amsterdam, for example, those coastal dunes are very important for the drinking water supply. Basically, they are the backbone. But these systems are at their limits, and we are looking to enhance these systems, and also we're looking for additional alternative water resources like brackish groundwater. I'm at KWR, a water research institute, but the pilot and the work that I'm going to present has been initiated by Dunea, which is the water utility of the city of The Hague, and it's.
I think you're muted now, Klaasjan.
Yeah. Okay. This should be good. click there, don't touch that. Hey, if you talk about the production process, the coastal dunes are very important, and they have a managed aquifer recharge system there. It's been in place since the 1950s. So what they do, actually, they take water from the River Rhine or the River Meuse. They can switch between those rivers, have that transported with long pipelines of about 70 kilometers to the city of The Hague, and then infiltrate that in the coastal dunes. And well, that system has been in operation. We have pre-treatment, of course, and post-treatment steps, and then the infiltration. And the system has been Jose, yeah, thanks. That system has been in operation for 50 years and longer. And the reason why we produce water that way in the Netherlands basically is this picture. This is a cross-section of the Netherlands from the east to the west to the coast. And you see in the red square, you see the coastal dunes, and you see that underneath the coastal dunes, there's a freshwater lens. That lens is where we produce our drinking water from. But all underneath, all the groundwater here is brackish or saline. That has to do with, well, the origin, the geology of the Netherlands being close to sea, but also being built by marine deposits. And so we have this very, well, relative thin freshwater lens under the dunes. We've been using that, but we have to replenish that with river water, because if we don't replenish it, we take out all the fresh water in the fresh groundwater, and salinization comes up. Now, these infiltration systems, they are beautiful as well. So they are integrated in the nature area. This is what an infiltration pond looks like in the coastal dunes. But basically, the systems are at the end of the maximum capacity. Climate change, low flows of the River Meuse and Rhine, especially deteriorating water quality, so that makes us not always able to take water from these rivers, and there's an increase in water demand because population is growing. And so what we looked at in this project is, if we extract groundwater from underneath that Mars system, can we enhance the functioning of that system? But also, and I think you may be interested in that, can we use that brackish groundwater as an additional drinking water source? So in normal operation, this is kind of a schematic. You see the freshwater lens that we use, that we replenish with this river water. And if we have an intake stop, we have to switch to deeper wells to produce drinking waters from. That's depicted in this picture. But the salt and brackish groundwater is very close. So once we start extracting water there, you have the risk of upconing. Now, I'm very much into water resources. I have a background in hydrogeology and how to manage these types of systems. And what you do, if you also extract the deeper underlaying brackish or saline groundwater, you can restore the hydraulic gradient, and you can make sure that, one, you increase that freshwater lens, but also prevent any salinization of that freshwater well. So this is what we tested in the whole freshman project, both the hydrogeology, but also, of course, if you extract brackish groundwater, it's a perfect source to produce drinking water from. This is what the whole pilot looked at. So both a subsurface part where we had extraction wells, both of fresh and brackish groundwater, a whole set of monitoring wells, and in the small building there, we had the RO treatment facility, where of course we did all these types of tests. Now, I just show you some highlights and brief results. First, some hydrogeology, and then I'll get to some results on the RO treatment. Well, this is a cross section going from top to down, deeper down in the surface, and in blue colors is where the water is fresh, and going to yellowish colors you go to this brackish and saline part. And you see a transition zone there at about 80 to 90 meters depth, where the end of this freshwater lens is, and we get into the brackish and saline groundwater. Well, this is before we started this pilot, and then we started extracting that brackish groundwater underneath. And what you see is, hey, such a lens, indeed, what we anticipated, is growing, is getting deeper. So we have more fresh water stored there, which of course is important for us. So that lens grew, but also we lost a lot of fresh water via mixing and in those brackish groundwater wells. So very efficient this was not. What we did then was okay, hey, we're going to test a bit, and we're going to extract only fresh water. So we extracted from shallower filters. And what you see in this picture, that you get immediate upconing of that brackish and saline groundwater. You know, those are the threats of these types of systems. And well, for me, this was a hydrogeological playground. So what we did then, okay, hey, we're going to extract brackish groundwater again, but we're going to combine that with fresh groundwater extraction and see if we can balance that fresh to saline interface and really make these things stable. And that actually really worked well. We could produce fresh groundwater without those wells getting salinized, and by extracting a small proportion of this brackish groundwater. Now, of course, you are probably more interested in okay, that brackish groundwater, you can use it. So we had experiments with reverse osmosis treatment. A two-stage system. We operated it at 50 to 65% recovery because we wanted to refrain as much as possible from any anti-scalants. We had a stream of, well, we had about 10 cubes per hour permeate production, but I think what is most interesting for you is that we had an anaerobic treatment. That groundwater is anaerobic. It also has a lot of dissolved iron, so keeping the oxygen out is really key to operating these types of systems. Now, well, my technology colleagues and water treatment colleagues, they were complaining it was kind of a dull pilot. You know, with this anaerobic groundwater, it's really good in terms of not having any scaling issues. And the main scaling issues was trying to keep the oversaturation of especially the carbonates under control. So some pictures on the well, conductivity, but also on the membrane pressure, and you know, with 50-55% recovery, we could really keep this stable without having any anti-scalant dosed. If we go higher in concentration or in recovery, then you get some first scaling. Of course, flux measurements. We also did some experiments, or colleagues did some experiments with fluxes over the membranes, well, to really get this system in place. Now, what is of course very important is the water quality of the permeate. If you want to produce drinking water, well, of course, ammonium, boron are elements that can partly pass membranes, because that was easy. But also, of course, if you want to produce drinking water, you have to think of we desalinize it, so we have to do something about the calcium, magnesium, and bicarbonates to get it to drinking water levels. And I think this is one of the most interesting part from the water treatment side and drinking water production. And that's the effects of mixing this permeate with the normal drinking water that is produced there. In the Netherlands, we do not chlorinate our drinking water. So if the drinking water goes into the network, no chlorine is added. And we can do it, one, because we have, well, moderate temperatures. So the water, you know, it doesn't get that warm. But also we make sure we have a very low growth potential for any bacteria. And in that way, we can keep the drinking water biological stable without adding any chlorine before distribution. But what happened if we mix the permeate with the drinking water? And remember, this permeate was produced from anaerobic groundwater. We had a lot of biofilm production. So actually, we had, in our terms, unstable biological unstable water, and we cannot use that and put that in the net. And so we did experiments with that and tests, and a lot were on methane and sulfide oxidizing bacteria. So we are further researching this, but the theory now is that those little traces of ammonia and hydrosulfuric acid produce a little source of these bacteria. These bacteria are in that water, and they are present in the drinking water, and we got biological unstable drinking water. So degassing there is very important. I think, yeah, this is my last slide. So I took you a bit into the groundwater and the subsurface. We can improve these managed aquifer systems, managed aquifer recharge systems, improve them, combining them with tailored brackish groundwater extraction. Anoxic groundwater, of course, an excellent feed for reverse osmosis treatment, keep the oxygen out, obviously. And that degassing was very important here, degassing of the permeate after you produce it. And I think, yeah, that's what I wanted to share with you today at this webinar. So, thanks.
We'll move on to the next presentation. I'll pass the floor to José Luis Cortina Pallas from EXBRINER.
Thanks, Micaela, and thanks to all the INDESAL project for this invitation. The project that I'm going to be presented is totally different. It's a doctoral network. It's a training people on research. And I'm going to do on behalf of the coordinator, that is Efrain Curcho from University of Calabria. This proposal on this doctoral network was built to develop activity in what we call circular blue industry, and mainly to focus on in which way seawater desalination brines could provide some value, provide more water to produce chemicals and to produce energy. And it was these three main vectors of development that were devoted to being working on process intensification, but developing new membranes, new materials, and new processes, and then to be validated on energy and chemicals production, and also trying to develop this concept of seawater mining. Then in general terms, but more specifically, the project that is incorporating 10 different universities and 4 industrial partners develop a concept where we have on the upper part of the slides that the new developments, this new generation of membrane technologies, were focused in 3 main areas. Is to be working on this concept of thermoplasmonic membranes. The second one is to develop membranes where the selectivity patterns are to such extent tuned by introduction of, let's say, molecular organic frameworks to introduce very selective ionophores like zeolites. And finally, been working on optimizing or improving the performance of ion exchange membranes and new ion exchange membranes that are also being developed in the project. Then those materials were focused to provide new solutions to something that for most of the audience is clear, that when we are starting having a seawater desalination brines, if we want to recover materials to produce chemicals, we need to make 2 things. Is one, to make some pre-treatment of the brine. Typically, this could be done by nanofiltration or by electrodialysis to reach one stream that is very rich in monovalent ions, and that is on the bottom, and on the upper part to have a very, very rich stream on divalent ions when we could recover, for example, magnesium. And this system to be, let's say, as blue as we want, or as more sustainable that we could think about, we need to relevant technologies, that is the use of reverse electrodialysis for the production of energy, as has been described previously in the two first presentations, and also, as was presented in the first project, the use of the bipolar ED to produce chemicals. Okay. Then, if you have in mind that now we have a very, let's say, we have a very stressing next minutes, because we have 10 projects or 10 ideas to be presented, and then I've been preparing one graphical abstract for each of one, and I think we will be able to do in the time that we have. Okay, the first project and the first be the students, because remember that the most important that you are going to be now see is the candidate that are going to be converted in a few time in new engineers to be starting working maybe in your companies. Is the work developed by Mohammed Hassan at Leuven University. And Hassan is trying to develop new nanofiltration membranes using a different polymer chemistry. Instead of using the polysulfone as a starting point for building the nanofiltration membrane, is to use polyacrylonitrile. And after, he has been working in the use of interfacial polymerization to develop the selective polyamide typical layer that we are familiarized on nanofiltration membranes. And then all the selectivity patterns are allocated to the use of these metallic organic frameworks or zeolites to put neither in the upper layer, or even this layer could be just located between the polyacrylonitrile or the polyamide layer. And this is going to be applied in the first stage of separating monovalent from divalent ions. Now move on to all the activities that are related to overcome the use of reverse osmosis, and then to try to use membrane distillation as a technology for increasing the water recovery, and also to provide the possibility to move to being working on recovery of salts by using crystallization. And we have this project from Alula Selemon from the Institute of Membrane Technologies in Calabria also, where the main objective is just developing membranes where the active layer is incorporating, let's say, graphene oxide to improve the photothermal properties, and to validate on the concentration of this brine to the water recovery and the crystallization stage. Also related to the use of membrane distillation is the work that is being developed by Ialuipolu in Politecnico de Milano and the Italian Institute of Technology, where also is devoted to enhance the properties of the membrane distillation technology. In that case, by incorporating the use of two-dimensional materials, where, for example, metallic and organic frameworks or other crystal nanoparticles are incorporated into the active layer of the membrane distillation. The third project, developed by Indira Kimandal at INSA Toulouse, is a more practical or more engineering application of this concept, where in that case hollow fiber membranes are going to be used in vacuum membrane distillation studies. The idea is directed to work on brine concentration for increasing the water recovery, and in that case incorporating solar energy as a source to achieve this concentration and crystallization stages. And the last topic in that area, developed by Tatsone Dadiani at the University of L'Aquila, In Italy, that is devoted, this is a more, let's say, fundamental study, is the use or the possibility to use XPS on the characterization of the membranes, of the processes that are occurring in the surface of the membranes, especially when you are working with membrane distillation and membrane crystallization. The work is focused on the lithium recovery projects, and the idea is to identify all these stages that are providing the possibility to reach the suitable nucleation and crystallization conditions. Okay, we move to the next group of students working on the development of ion exchange membranes and applications. We have here the first case of Mecca Venio working at the Nova University in Lisbon. She's work is focusing in using 3D printing to develop these profile ion exchange membranes you have on the bottom. She has been working on developing both cation and anion exchange membranes, and here you have on the bottom the detailed structures. Try to create these profiles using neither stripe or these chevron units, and the work is now being validated in different applications, even from the hydrogen production and other in reversal electrodialysis and also in electrodialysis. The next project that is developed by Federico De Sommi is working at UCT Prague, where there is a group, it's a technology group focusing on modeling and characterizing ion exchange membranes and the performance of these systems. And then he's going to be develop the validation or these new ion exchange membranes and another ion exchange membranes that are going to be developed by incorporating metallic organic frameworks. In the same direction, it should be mentioned the work being developed by Anastasia Lima here in our department in Barcelona. She has been focusing on the application of ion exchange membranes and bipolar membranes in the on-site production of chemicals from sodium chloride brines, and especially is focusing these first stages on understanding what is the effect of the temperature. We have been seeing that typically most of the membranes are characterized, let's say, at root temperature. But as was commented by Mariana, is evolution of temperature, for example, in these pilots along the piloting work moved from neither, let's say, this some winter temperature below 20 to close to 30 in summer operation, and other industrial process where even the temperature of the operation of this stack could be reached up to 40 degrees. And just to finalize, if I could, Michael, I have three last projects. There are the ones that are working on more, let's say, industrial applications of these technologies. And then I should mention first the work that is developing, but that is out at the Aalborg University, where is working on the use of membrane distillations to demonstrate the production of magnesium as a magnesium sulfate or lithium as a lithium carbonate from the brines generated from seawater desalination brines. The work that is being developed also by Robiel Berjani, working at the University of Calabria. It has been integrating the use of both membrane distillation as a pre-concentration stage, and after, in a second stage, ED or ED bipolar for the demonstration of the production of lithium hydroxide and lithium carbonate. And that's all. I think I was a little bit over the time, but I hope was clear, and remember that from this project the most important are those students developing this training work in a near future to be just probably working with you if you need these new engineers. Thanks.
Thank you so much, Jose Luis. And no worries, we have still around 15 minutes for the Q&A session. So we can move for that. Okay, I think the first part of the questions are to Patricia, since her presentation was first. So the first question is, in a potential implementation of the technology at full scale, what impact could the energy produced have on reducing total energy consumption and OPEX?
Okay. Well, taking into account the total maximum energy production or obtaining in Alicante and the total energy efficiency, we have estimated an important reduction in the total energy consumption, specifically with a 0.3 kilobytes hour by cubic meter of brine and an energy efficiency of 30%, we could reduce the energy consumption in 12% of the overall process. The reduction in the OPEX is dependent on the energy. No, and the cost of the additive, of the maintenance of the additive. But in general, a total reduction of 12% in the total energy consumption.
Okay, thank you. The next question is also to you. Thank you for the presentation. Did you use any pretreatment for the effluent of the WWTP, and did you see any fouling, maybe related to a lower energy efficiency?
Okay. Yes, we implemented a pretreatment of the wastewater. No, that is such a tertiary treatment of a wastewater treatment plant. Why? Because we pump the treated wastewater directly from the effluent pipe discharge from the wastewater treatment plant to the sea. So we install a pilot plant to pre-treat the treated wastewater before introduce it to the additive process, and we implement as such a pretreatment a sand filtration. And with this process was enough to obtain a high quality of the treated wastewater to feed it to the membranes. We obtain at the output of the sand filtration a turbidity less than 1 NTU. And it was enough. And during our experimentation, we haven't observed any fouling in the membranes. So the pretreatment works correctly.
Thank you, Patricia. I'll jump to a question to Klaasjan. Thank you, Klaasjan. Super interesting. I wonder, how do you assure the reverse osmosis is operated anaerobically? And also if for the justification of the produced permeate before mixing, you have considered membrane contractors. Thank you.
Right. Yeah. Yeah. No, I'm not the right person to ask these questions, as I'm not a technologist. But this is the third pilot that I've been involved in where we use brackish groundwater, anoxic brackish groundwater for reverse osmosis treatment at 3 drinking water companies, and all the technicians have been complaining that the pilots were very, very dull because we did not have problems with there weren't any problems with fouling and such, but also we were able to keep the oxygen out. Also, the greenhouse industry in the Netherlands, they have been for about 20 years they have been using anoxic brackish groundwater treated by reverse osmosis, doing the same trick. So I'm sorry, I don't have the details, but it seems that it's quite under control. Well, as long, I assume, you have your whole system both from groundwater pumps to distribution, that you have it well in place and well maintained. I assume those are the most important. Of course, we did put in some cartridge filters and some other early warning systems that would help us. Once there would be a leak of oxygen into the system, then the system would shut down immediately to prevent oxygen reaching the membranes. Now on the degassing, this is still research going on how to best do this. Is this really the theory we have? Is that really what is going on? So we haven't moved forward there. So we're not in the stage yet to contract any tech providers for that.
Thank you. There's another question to Klaasjan. Do you consider to pre-treat the underground water using biological technology, for example, biofiltration, to allow the bacteria to oxidize iron and avoid problems in a RO system, plus opposed microfiltration? And maybe the biofueling problema could be attacked using biotechnology.
Yeah, well, we have not considered that, and I doubt if we will, because there are so many advantages of keeping the groundwater anoxic, just having this anoxic RO treatment, that we do not want to do any pre-treatment there. So just for now, the simplest solution for us is to get rid of those traces of methane and H2S in the permeate just by I don't know how we do it, probably ventilating or bubbling or something. So we do not want to do any pre-treatment to the groundwater that we're using, just to keep this process as simple as possible here.
Thank you. I'll ask a couple of questions to Jose, keeping the time in mind. Hi, Jose. What could be... Oh, do you hear me?
Yeah.
Okay. What could be, in your opinion, the main value of the EXBRINER PhD training network in terms of industrial partners in the seawater desalination and brine mining sectors?
Okay. I think from us it's been a very good experience, recruiting scientists and engineers in the area of desalination, and I think in general is quite difficult. And I think this project is having the opportunity to incorporate very skilled engineers and being trained in topics on seawater mining. And I think that the value for the European industry is, I think, we are expecting is going to be high.
Thank you. Let me see. Okay, we have another question to Patricia. Thank you for the great presentation and very encouraging results too for further development of this technology. You indicated a change in membranes. Could you maybe indicate what membranes you have used changed? Will there be a more in detail result reported on the strength weaknesses of these membranes? Thank you. We can hear you, Patricia.
Hi. Can you hear me?
Yeah.
Okay. Sorry, I don't know if I understand properly the question.
I can repeat a few.
Oh, please, Michaela.
Yeah.
I haven't said
So, you indicated a change in membranes. Could you maybe indicate what membranes you have used or changed? Will there be a more detailed result reported on the strength or weaknesses of these membranes?
Okay. Well, we don't want to share the specific model and developer of the membrane. The membranes have been installed by REDStack. Hendrik is going to present later the company and the difference between EDR and EDR. and they implemented the membranes in the stacks. So I only want to say that it was more efficient membranes with more compact designs, and which we will be improve the energy efficiency of the process.
There's another question. What was the pretreatment needed for the treated wastewater used as feed of the REDStack? Could you comment on that?
No, it was only a sand filtration. We installed a pilot plant with two columns of sand operating in parallel, and which we obtain an important reduction in the solid total suspended solids.
Thank you. Another question to Klaasjan. That seems like a succeed pilot for a solution for a drinking water provision. Is anything already known about the rise in drinking water production's costs due to this new method? And a second question, the dune system of Dunea is one of the most heavily protected Natura 2000 sites. Do you foresee that with an upscale solution that installations could be placed further away from the protected sites or can be integrated in the current infrastructure?
Yeah. Well, about the production price alternative, in the Netherlands, we are desperately looking for additional alternative water resources. They will be more expensive than our current drinking water systems. Though the managed aquifer recharge site also is it's not a cheap way of producing drinking water if you compare it to like regular groundwater extractions, for example.
There's a small addition. They meant the rise in drinking water costs, not production.
I have to understand the question better then.
Is anything already known about the rise in drinking water costs due to this new method? I think that's the correct question.
Yeah, for Dunea as a whole, the drinking water cost would not really increase that much. As is the way managed aquifer recharge to produce drinking water is also not it's not very expensive, but it's still not the cheapest. It's cheaper than Desal, seawater Desal. I think the other question, the latter part of the question is indeed very important. This is an important Nature 2000 area. If you pump brackish groundwater, you still pump groundwater. And we've done a lot of modeling work on if we would apply this at really full scale, and then the effects on the phreatic groundwater levels and on the nature reserve would be too big. So in terms of upscaling this at this Dunea site, not in the same amounts that we had in mind prior to the project, but for Dunea, the whole what we learned about the pilot is really applying this to smaller scale and really as a preventive measure for salinization. So we had to lower our ambitions there because indeed this is a Nature 2000 area with effects on groundwater.
Thank you. Let's see, we have 1 more minute to spare for questions. Question to Patricia. In the trials with wastewater, have you analyzed the presence of emerging contaminants and their behavior in the RED process?
Yes, we have analyzed it. We analyzed the presence of micropollutants, of contaminants of emerging concern in all strips involved in the projects in order to study the potential crossover from the treated wastewater to the auto brine. In fact, as we estimated, there's a crossover, a pass of these micropollutants from the treated wastewater to the brine. but carrying out or doing the total balance of the micropollutants, we have observed a short retention of the micropollutants of the membranes. Is that to say, not the 10% of the emerging contaminants pass through the brine. We have observed a short retention in the membranes.
Mm-hmm. Perfect. Thank you so much, Patricia.
Yeah.
And with that, I think we're gonna wrap up this block, and we can move to the next session, which is the Desal Innovation Showcase. And our first speaker is Marina Martinez from Universidad de Cantabria. Hi again, Marina.
Hello. Okay, so, well, good morning, everyone. My name is Marina, as Michaela said, and I work in the University of Cantabria as a research engineer. And within the Life INDESAL project, the role of the University of Cantabria was to design the EDBM unitary process to be integrated in the whole pilot plant of the project. And today, I would like to make a short overview of the EDBM technology and make a short discussion on its application and its potential within the desalination technology. So first, I would like to make a brief description of the EDBM technology. The electrodialysis with bipolar membranes is an electromembrane technology that can convert salt concentrates into acid and base by applying an electric field. And well, the core of this process the main unit is the EDBM stack. As you can see on the left, a scheme of the EDBM stack, which is composed of ion exchange membranes and bipolar membranes that are assembled between two electrodes where the current is applied. Well, as the name of the technology suggests, the key component of this technology is the bipolar membranes that are able to split the water molecules into protons and hydroxide ions when the electric current is applied. So as a result, we have 4 different compartments in the EDBM stack: the salt feed, the acidic solution, the alkaline solution, and the electrolyte rinse solution. So for the desalination application, the most common use of the EDBM is to valorize the brines to produce hydrochloric acid and sodium hydroxide. And well, the EDBM can be applied in desalination to produce these products to its direct use within the desalination plant, or the EDBM can be integrated within broader brine valorization strategies. But in the case of the Life INDESAL project, the objective of the EDBM unit was to produce sodium hydroxide and hydrochloric acid for cleaning operations and pH adjustment in the LMSRO unit, thus avoiding the external supply of these chemicals in the plant. So, well, here you can see a very basic layout of the EDBM process where the acid and base operate in batch mode, recirculating the streams until reaching the desired concentration of both chemicals. And in this case, the brine that we were using to feed the EDBM comes directly from the LMSRO. And the LMSRO process has the particularity of they use real seawater, and the content of magnesium and calcium is not, well, they have a significant concentration in the brine. So these ions are not recommended for the EDBM operation because of pH higher than 10. Normally they tend to precipitate in form of hydroxide, magnesium hydroxide, or calcium hydroxide. So these ions can cause undesirable phenomena as an increase in the electric consumption, also scaling phenomena or obstruction in the system. So to address these issues, we installed a pretreatment stage consisting of a nanofiltration step to reduce the quantity of concentration of the magnesium and calcium. We almost reduced an 88% of magnesium and 67% of calcium from the brine. And as we did not remove the whole magnesium and calcium ions, we also implement a maintenance strategy to reduce the possible problems caused by this magnesium and calcium by consisting of a periodic acidic cleaning of the whole system and a control of the pH. So with this approach, we could operate under stable conditions and no operational problems related to the process of this magnesium and calcium ions were observed. Well, regarding the production performance, we reached the target objectives in terms of production of both sodium hydroxide and hydrochloric acid in the plants. So beyond INDESAL, the EDBM has been already applied in other desalination related projects, and I would like to mention a couple of these examples of application. The first project I wanted to talk about is the water mining project. Well, the main objective of this project was to recover minerals and critical raw materials from brines and other saline streams. And in this project, the EDBM was applied to produce sodium hydroxide, which was used internally for the magnesium recovery under precipitation. So in this case, the production of sodium hydroxide was not used for the cleaning operation, but for the recovery of magnesium. And another project I would like to mention is the C4 Value project. This project also focused on the recovery of valuable minerals and metal from desalination brines using different technologies. And of course, these technologies included the EDBM. And in this case, the EDBM was used for recovery of boron from brines applied to produce boric acid. So these are two examples that really highlight the versatility of EDBM as a technology for brine valorization in the desalination technologies. So to finish the presentation, I would like also to briefly mention some emerging applications of EDBM that are still in early research stage, but they show strong potential for desalination application. One of these applications is the energy storage through acid-based flow battery. In this concept, the conventional EDBM is used in the first phase of the technology, where we called charging phase. This is application of conventional EDBM to produce acid and base using a concentrated saline solution as feed. And after that, after the charging phase, during the discharging phase, reverse EDBM is applied, where we feed the systems with acid and base, concentrated acid and base, to recover the electrical energy stored. And the other promising application of EDBM in the future is the hydrogen production using EDBM. As well as we know, in the electrodes, we produce hydrogen and oxygen. And as we know, hydrogen it's now a trend, and also we can use it as a byproduct of the EDBM technology. Some studies have already monitored the production of this hydrogen in the electrodes, and some of them reported hydrogen productivity up to 18.4 moles for the hydrogen of per hour and square meter. So that's all from my part. Thank you very much.
Thank you, Marina. Our next presenter is Hendrik Swart from REDStack.
Thank you, for the introduction, Michaela, and the opportunity to present something about our electromembrane stack technology. Are you able to see the presentation correctly and also hear me fine?
Yeah.
Great. Yeah. All right. Good morning, everyone. My name is Hendrik Swart, and today I will be presenting the advancements REDStack has made with electromembrane stack technology. Mostly what we have done is research and develop a novel design to improve the efficiency and scalability of electromembrane electrochemical processes and technologies to help industries save on water, chemicals, and costs. Just briefly going into what we changed to the stack design is the most important thing is that we have externalized the flow distribution. So we have a membrane area which is square, which is, you can see, is the red square here. And we have externalized the flow distribution to better optimize the use of the active membrane area, but also to improve the flow distribution inside of the membrane package, reduce ionic shortcut currents, and overall improve the efficiency of the stack. And what we then make are basically these circular discs with a certain amount of membrane area inside of it. And these discs we can stack together and assemble them in a electromembrane stack. Depending on the treatment capacity that is required, you can add more or fewer of these discs. And then thanks to this design, it's a lot more energy efficient. And for applications for desalination, so electrodialysis, we can see a 50% lower energy consumption compared to conventional stacks that are in the market. We are focusing on 3 different applications where we want to implement our innovative electromembrane stack design. The first one being reverse electrodialysis, so the production of renewable energy. Second is the electrodialysis reversal, or brackish water desalination, or a very upcoming and hot topic is brine treatment. And the third application is electrodialysis with bipolar membranes. In the previous presentations, already something has been presented on RAD and EDBM, so I will give you some examples of electrodialysis reversal. But before I go into detail, I will give you a little bit more insight on how the process works, and also to maybe clarify some things, because there's often confusion between electrodialysis reversal and reverse electrodialysis. Even though there are a lot of similarities between these 2 technologies, they are not the same. And in fact, they are the opposite of each other. And I will start first with the electrodialysis reversal technology. This technology is used for desalination. It's an electrical driven desalination technology to remove ions from water. And you do it with the use of a device called a electrodialysis stack, or what we refer to a electromembrane stack. It consists of 4 components: anion exchange membrane, cation exchange membrane, spacers, and electrodes. And the membranes allow the selective transport of ions. So if we then feed water through this system, we introduce ions. In this case, on the screen, you can see sodium and chloride. Then we apply a potential to the electrodes, and the ions are transported towards the opposite charged electrode. And in this way, you create compartments that are being concentrated, so salt is transported to them, and we have compartments where the salt is being removed from, creating a dilute stream. And the reversal then comes into play when we reverse the potential. What meaning is that we can reverse also the direction of the current, and that means that we reverse the direction the ions are transported to, and the previously concentrate compartment becomes a dilute compartment, and vice versa for the dilute compartment. And this way, it's a self-cleaning process because it helps reduce profiling and also scaling, and it overall improves the efficiency and the lifespan of such a device and process. Then coming to reverse electrodialysis. As the name suggests, it's the reverse of electrodialysis. So let's have a look. Here we have the same hardware. We use the same materials. Again, the membranes, anion exchange, cation exchange spacers, and electrodes. But in this case, we feed two different feed streams, one with a low salinity and one with a high salinity. And then if we connect the two electrodes together to close the electrical circuit, we allow the ions to be to move from the high salinity towards the low salinity stream, and this creates a ionic current. And this ionic current is then converted into a useful electrical current at the electrodes, and in that way we produce sustainable energy from mixing two streams with a different salinity. And then we end up with a mixed solution of brackish water. So now I would like to give you some examples of how EDR can be implemented for desalination. First on brackish water treatment. And if I'm talking about brackish water, this is typically water that has a total dissolved solids content below 5,000 ppm. And a very large application of ADR is then the tertiary treatment of treated effluent to create irrigation water. Is a lot of used in the Canary Islands and also in Spain. So here we have the effluent from domestic effluent. If we were talking about producing irrigation water from it, but we can also treat industrial effluent. In most cases, there's some sort of pre-treatment required to remove the suspended solids and the organic materials that are still present to avoid fouling and clogging of the electromembrane stack. Then we have the real technology to remove the salt. And with EDR, the advantage is that we can steer to the required product concentration or quality by putting in more or less energy. And then we create product water. In the case of treating domestic effluent, we can create irrigation water, but also within industrial applications, we can treat industrial effluent and then polish it to process water again. And I have one case study I want to quickly go into detail. This was performed by us in the Netherlands at a horticultural wastewater treatment plant. So a lot of greenhouses were discharging their water to this treatment plant where they removed the pesticides before they could discharge it. But they also had issues with chlorides and nitrates. And that's where we came into the picture with our desalination technology. And I want to mostly highlight that we have a two-stage system where in each stage we can remove up to 60% of the salt, ultimately achieving a maximum desalination of 84%. And in this case, it was required to remove 75 up to 80% of the salinity. But the very nice results were that if you look at nitrate removal, that there was a selective removal of nitrate over chloride. So with a removal of TDS of 80% or 75%, we could achieve a nitrate removal of over 95%. And then the other application I want to quickly touch upon is the application of EDR for brine treatment. It's most commonly used to improve water recovery of other desalination processes where they use RO, or to go to a zero liquid discharge. So here we have then the brine coming from desalination or another water treatment process. Mining or textile industry also has a lot highly concentrated brine streams. Then we have again pre-treatment to remove the suspended solids, organic material, and optionally softening to remove calcium and magnesium, because if you want to go to very high water recoveries, you get problems with scaling. So you remove the calcium, magnesium. Then the EDR is implemented mostly to further concentrate this brine stream, to increase the concentration of the brine and reduce the volume. The produced product stream could then alternatively be used again in the process or treated again. And the concentrated brine stream is then going through a thermal treatment process for example, evaporation or crystallization to achieve zero liquid discharge. This is all I had to present for you. I hope you found it interesting, and thank you for your attention.
Thank you so much, Hendrik. Our next presenter is Juan Manuel Ortiz from MIDES.
First of all, thank you very much for inviting me to this seminar because it's quite interesting. So I'm going to explain the things that we are doing at INDESAL related to this MIDES project, Microbial Desalination for Low Energy Drinking Water. Is something completely different because what we are trying to do is to mix biotechnology with desalination in order to explore if with this approach we can do something interesting in the wastewater treatment sector. The things that we are going to explain are related to the MIDES project. MIDES project was a project from Horizon 2020 program, and the coordinator was Aqualia, and INDESAL was involved in the development of this new microbial desalination technology. Okay, so first of all, INDESAL is a technology center in Madrid. And it's a research center focused on the water sector. So we have different levels. We have groups focused on water quality, some other groups on environmental studies. We have groups also working in technology, in water technology, and also we have economists and people related to economics of water and also governance of water. So what I am researcher there at INDESAL, and I am working in BOE group. It's a group. What we are doing there is environmental biotechnology, and especially what we are doing is microbial electrochemistry. That is the study of interaction between microorganisms and electrodes. So as you can imagine, is something in between microbiology and electrochemistry. And with this new field of research, what we are doing also is to try to develop microbial electrochemical technologies for wastewater treatment. So just very simple, when you have microorganisms, anaerobic microorganisms, for example, these microorganisms in the natural environment, what they do is the oxidation of organic matter. Then the oxidation of organic matter, they extract electrons. They use the electron for the metabolism, for example, production of energy, ATP. And after this process, they have a low energy electron, and they need to release this electron again. No? So there are some microorganisms that are able to use as final electron acceptor iron 3 oxide, for example. It's a solid electron acceptor, and they use this electron, or the iron 3 is you have the reduction of iron 3 to iron 2. No? So with some imagination, you can put these microorganisms inside an electrochemical device, and what you are going to have is a microbial fuel cell. The point here, or the key, is that you can put these microorganisms in another compartment, and as long as you provide wastewater or organic substrate, they are going to do the oxidation of water. The oxidation of organic matter. They are going to put the electrons in the electrode, a biocompatible electrode like graphite, for example. It's possible to produce some energy. And the electron is going to be combined in the catholyte, for example, with iron 3, a solution of iron 3. And obviously, it is necessary to put a membrane in the middle, an ion exchange membrane, to separate the anodic environment and the cathodic environment. it's quite good to be here because I don't have to explain anything about the ion exchange membrane because you know all about that. So the first, and this is the microbial desalination cell. If we include an additional membrane, what we have is something like, it's a mix between a microbial fuel cell and an electrodialysis system. So you can imagine that you can put here a saline stream, saline water, and because of the electric field inside the device, you are going to have the migration. Obviously, the current density of operation of this kind of system is not like the electrodialysis system that you mentioned before. Normally, electrodialysis system works with a current density of 10 or 15 milliamps per square centimeters. What we have here is a system that provides current density around 1 milliamps square centimeters. So the first definition of this concept was in 2009 by Cao in Penn State University. And well, I have here a nice slide just explaining what is the electrodialysis system now. And in this project, what we use is the electric field provided by the microorganisms. So what is the point with this? The point is that it is possible to do the desalination of seawater or brackish water with less energy. So because what we are using is the energy that is contained in an organic substrate. No? So in the left part of the slide, you have the energy consumption of normal desalination or state-of-the-art desalination system like reverse osmosis. That is something like 3 kilowatts hour per cubic meter. And obviously, using microbial desalination, it's possible to do the seawater desalination using less energy. Because what we do, or let's say the objective of MIDES project was to use this biotechnology, these microbial desalination systems for decreasing the energy consumption in conventional pilot plants. The idea is to use microbial desalination to do the pre-desalination of seawater and produce brackish water from seawater. Obviously, if you want to do this, you need a substrate, organic substrate source, no? For example, wastewater or wastewater from food industry. This is the kind of system that we are using for the study at lab scale. It's a conventional filter press cell, in which you have membranes, electrodes. The electrodes are graphite, and the membranes could be used conventional ion exchange membrane, homogeneous or heterogeneous. You have here, that is very interesting, in the left part of the slide, this tank with a pink solution. This pink solution are microorganisms, especially Geobacter sulfuroducen. This is the model microorganism that we use to do this kind of experiments. And well, some figures explaining a bit what we are doing in the laboratory. This is in the left side, you have this microbial desalination cell, a diagram. We have in the anodic compartment the microorganisms living in the electrode. The electrode is graphite felt. The saline compartment in the middle, and in the cathodic compartment, we can use different electron acceptors, a redox mediator like ferroferricyanide, or maybe oxygen. So different electron acceptors in the cathodite provides different performance of the system. But what is very interesting here, in the right side, you can observe the nominal desalination rate with this system for brackish water and seawater. If we use ferrocyanide with brackish water, we can obtain a nominal desalination rate around 1.5. That is not bad. But the interesting thing is that we can obtain energy if we want as well. The specific in green, you have the specific energy production in kilowatts hour per cubic meter. So with this kind of system, it's possible to produce, for example, using seawater and oxygen, for example, something like something like 5 kilowatts-hour per cubic meters. So I write down the level of kilowatts-hour using a blue energy system that is around 0.2. So it's possible to obtain a bit more. Obviously, depends on the operational conditions. You have here 2 experiments. Well, if you are interested in scientific papers, you can check this paper from Marina Ramirez that she did the PhD at INDESAL using this kind of systems. And this figure is similar. You can observe for brackish water the COD removal rate, that is the velocity of wastewater treatment, and also the specific energy is around 1.4, 1.6. And the final outcome of the MIDES project was the scaling up of the MIDES system. In the bottom of the left side, you have the small reactor. We started with this small reactor at lab scale, and after different stages, we were able to produce 2 pilot plants. One of the pilot plants is doing experiments in a desalination plant for brackish water in Denia, Alicante, in Spain. And the other one is in Canary Island, in South, in Guia de Sora, trying to validate the technology for seawater desalination. If you are interested in the project, we have an open access book published by IWA. So you can check the book if you're interested in this kind of systems. And also another thing that I would like to comment is my last slide, is that we are also testing this technology in a wastewater treatment plant for brackish water desalination at the end of the wastewater treatment plant. In order to change the salinity for agriculture uses. No, this project is in. We are developing this project in Murcia in order to reuse the water coming out from the wastewater treatment plant. And that's all. Some of the companies that thanks a lot for the invitation. Thanks also to the institutions that fund our research, and also the companies that believe in this kind of environmental biotechnology approaches for sustainable desalination. And that's all. Thank you so much.
Thank you so much, Juan Manuel. Great presentation. And we'll move to the next speaker, Alberto Maimone. Yeah. Hello, Alberto.
Well, firstly, I would like to thank you for inviting us to present our work in this event. Today, we will be discussing some concept, experience, and challenge of electrochemical technologies, specifically capacitive deionization. Well, the accelerating degradation of water reserves and short age of Raat materials are 2 of the main challenges facing European countries. And therefore, obtaining fresh water and Raat material from alternative and unconventional sources is key solution for resolving these subject issues. In this context, several solutions have been studied, including membrane technologies, natural-based solution, and electrochemical technologies. Okay. In all capacitive sectors, a voltage is applied between 2 electrodes, which can be immersed directly in the stream or can be separated from the stream by membranes. Generally, the capacitive process has two stages, charging and discharging stage. First, during chargings, the applied voltage create an electric field that attract anions and cations to the respective electrodes. Then, depending of the process, one or two options is possible. No. Filtering at the absorption stage, they take place once the solid electrodes become saturated, during which the applied voltage is reversed. During this stage, the ions can be released to the concentrate stream, other stream. And the second option is involves recovering these ions from the flow electrode through a secondary process, such as electrochemical or chemical precipitation outside of the cell. Okay, the capacitive process can be controlled by a non-Faraday mechanism that involves a molecular rearrangement on the electrical double layer, which are not controlled by mass transfer. On the other hand, the capacitive process can be limited by Faraday mechanism, which include charge transferred. It can either be diffusion limited, intercalation, or not diffusion limited, pseudo-capacitive. This aspect are so important and must be considered to improve the efficiency and selectivity of the capacitive process. So, SETIM has worked in different projects, and specifically, SETIM's work in REWISE project focus on recovering lithium from desalination brine using capacitive deionization with lithium iron phosphate electrodes. This active material was recovered from battery waste by direct regeneration that include mechanical, chemical, and heat treatment under reduced atmosphere. In the table, we can see the initial composition of the brine used. Okay. So, the effect of the flow rate and current density on charging and discharge and discharging stage was evaluated. It was found that while higher current density increases electroabsorption of all ions. However, the selectivity decreased. In this sentence, we can observe a downward trend in the selective factor when the current density is increasing. In general, we can see that the selective factor was higher of less current density, around 15 million per square centimeters, with values of 15 for lithium and sodium, respect to the sodium, 9 for lithium respect to magnesium, and 2 for lithium respect to the calcium. In general, this valued or well. On the other hand, the current density effect on the release stage was evaluated too, achieving a concentration factor around 4 for lithium, while this value for other cations was less than 1. In summary, lithium concentration has been achieved with good selectivity with respect to the main impurities in this brine, sodium, magnesium, and calcium. Other projects like Resurgence, we have applied a different configuration setup. In this case, we use flow electrode to treat an industrial stream using different metal organic framework as active materials, such as zeolitic imidazole framework and copper hexacion ferrate, Prussian blue, among others. We can achieve both relevant factors, salt absorption capacity and average salt removal rate from simulated industrial brine using SIG8 as the active materials. This work on the Resurgence project is ongoing right now, and these values aren't definitely. Okay, among the main challenge facing capacitive technologies is improve selectivity to achieve this. It will be necessary design materials with a specific pore structure and maybe to make superficial modification to improve chemical affinity to with respect the target ions. And also it will be necessary to improve the stability of the electrodes by using more stable active materials that interact reversibly with ions in the electrolyte. And finally, a solution like flow electrodes could improve operational condition, resulting in lower cost and maintenance. It's all, and thank you for your attention.
Thank you so much, Alberto. We're a bit over time, but we'll still have some time to ask some questions to the speakers. All right, let's see. We'll start with Marina. So, Marina, did you evaluate alternative treatment strategies for the removal of divalent ions from the brine prior to EDBM?
Yes, we did consider different alternatives to reduce the content of mainly magnesium and calcium in the brine. We evaluated the nanofiltration that we finally implemented, but we also thought about implementing ion exchange treatment. But well, in this case, the high salinity of the brine, it would require very frequent cycles for regenerating the resins. Even we made some estimation about how frequent would be that regeneration, and the main or the mean time to do it, it was going to be between 1 and 2 hours. We would need to regenerate the ion exchange resin. So this was operationally unfeasible, let's say. And we also thought about precipitating the magnesium and calcium, but with this strategy, we would need additional steps as filtration and centrifugation, and taking into account the reduced space we had in the container and in the pilot plant, it was not possible to containerize all these steps to precipitate the magnesium and calcium. And in both cases, in the precipitation and in the case of ion exchange, the two processes will need a consumption of a large amount of different chemicals. So since one of these projects objectives is to minimize or to avoid external supply of chemicals, we thought that the best option was to implement an filtration step.
Thank you, Marina. The next question is to Hendrik. Thank you for your presentation. From your experience when selecting brines for RED, is TDS or conductivity the main parameter to assess the energy potential apart from the absence of unwanted calcium and magnesium, or does the specific ion composition of the brines make a difference?
Yeah, there is a clear impact of the ionic composition on the potential energy that is available in the brine. Mostly multivalent ions impact the electrical resistance of the system, introducing more energy losses, and also reduces the potential energy. So if we're looking at when selecting brines for RD, you want, and also important to know, you also need a low salinity, and the biggest impact is the gradient between the two. The higher the gradient between the high salinity and the low salinity, the more energy you can recover. But of course, the ionic composition does make also a quite significant impact.
Thank you, Hendrik. The next question is to Juan Manuel. What is the current production of microbial desalination cells compared to reverse osmosis systems, and what production is needed to consider a microbial desalinate cell technology is fully developed for real application?
In few words, the production of a microbial desalination cell is quite low compared to reverse osmosis. We can say that maybe the reverse osmosis is between 15 or 20 liters per square meter an hour. And this kind of system produce more or less 1 liter per square meter an hour. So it's the good point is that you don't need energy as long as you have organic substrate available for desalination. And about the production, with the MIDES project, we are now in a production of 2 cubic meters per day, around this number. And we consider that we need to apply for the next project and try to develop to do the scaling up of the technology in order to have something like 100 cubic meters per day. So this is our objective at the moment.
Perfect, thank you. Alberto, how selective can capacitive deionization realistically become, and what limits the selectivity?
In order to improve the selectivity, it is recommendable to incorporate anion exchange membranes or functionalize the surface of the electrode and control of the pore structure to improve the interaction and transport between the electrode and ions on the electrolyte. In my opinion, the use of MOF has opened the door to truly achieving competitive selectivity. But there is still work to be done in this regard.
Perfect. Thank you so much, Alberto. I think we have time for just one more question, and then we'll need to move to the closing session. A question to Hendrik. Can the application you presented also be combined with systems for the removal of medication residues from wastewater? Second question. It is mentioned a lot of times your system has a much lower energy need, more efficient. Is there somewhere an overview of this comparison of energy use with other methodologies?
Yeah, thanks for the question. Very interesting. In regards to removal of medication and the residues from that, it's of course, if these medications have a charge, potentially they could be removed with electrochemical processes. However, in most of these cases, you want a physical barrier between your feed water and the produced water, and this is not the case with EDR because we do not we transport the salts from the one compartment to the other. So there is still no physical barrier between the feed water and the product. Though in most cases, if you look at these applications, then the clear answer is to use RO. And in terms of the energy consumption, it's a bit of a difficult question to answer because for EDR, the energy consumption is directly related to how much salt you want to remove. So for saltwater applications, so if we would compare to RO is the state-of-the-art technology, and EDR would not be able to be competitive there. But if you look at brackish water desalination or low water with a very low total dissolved content, then we can see a significantly reduced energy consumption, and that can be up to 50%. But yeah, depends on the specific feed water.
Perfect. Thank you so much, Hendrik. Unfortunately, I don't think that we have enough time to answer all of the questions. However, if some of the questions are still unanswered, and they are, we'll send the answers to all of the questions with a follow-up email to all of the participants and registrants. And now I'll pass the floor to Olga Ferrer to do the closing remarks.
Thank you, Micaela. I think that along this morning, we have been able to see different solutions and approaches to ensure a sustainable response for the same challenge, which is water scarcity. And we have been able to see some successful examples of approaches to supply alternative water resources. We have started with the managed aquifer recharge, with the example of Dunea, with the particularities of the anaerobic reverse osmosis. Then moving to desalination, either in seawater or for brackish water, we have seen the examples of LMSRO presented by Mariana with the INDESAL approach to reduce the energy consumption, the electrodialysis reversal commented by Hendrik, microbial desalination, also tackling energy consumption with the example of the MIDES project. And also we have gone through the opportunities raised by desalination by means of valorizing the brine produced. We have seen some great examples of increasing the recovery of water, for example, by membrane distillation, membrane crystallization, or EDR. Also another approach of obtaining energy from the saline gradient with the examples of HyReward project using wastewater and brine from a desalination system, but also in the case of INDESAL with the brine of the desalination plant. And finally, we have seen also some examples of resource recovery from the brine with the chemical production, as mentioned by Marina, with acetam base that can be used in the same facilities, but also the recovery of raw materials with the large set of examples of EXBRINER, recovering lithium, magnesium, rubidium, etc., reminding us the exciting world of the synthesis of leading edge membranes, tailor-made, just tackling the compounds that are really needed. So thank you all for the excellent presentations. We have had the chance to see today the future trends in sustainable desalination. I think that they have been quite diverse and inspiring, and they also show that thanks to collaboration, we are able to make progress from R&D to application, and then making a after a long some time some impact to the society and the environment, which is the ultimate goal. So thank you again to all the speakers for the great work, the audience for joining us today, and also the EU for funding all these projects. Thank you all, everyone.
Thank you, Olga. And I think with that, we'll wrap up our webinar. Thank you again for all of the presentations, all of the insights to the speakers. Thank you to the participants for asking the questions. And I would also like to remind everyone that we will be following up with you with the recording, with the unanswered questions. And we also encourage you to stay in touch with us, to stay connected with the Life in Desal project, even though it's ending. Stay in touch with the rest of the LIFE projects and all of the other projects that contributed. And we encourage you to explore opportunities for replication, collaboration, and knowledge exchange, of course. With that, we officially conclude the final event of the Life in Desal project. It's been a pleasure. Thank you all once again for being with us today. And I wish you a very pleasant rest of the day.
Thank you so much.
Thank you.
Bye-bye.
Thank you very much. Enjoy your day.